Hello, dear ladies and gentlemen. My name is Alexander. Today I want to talk about my research that I will be doing on Slinki, the following Slinki. So first of all, we put the highest part like at the stationary position, and later we see how mass distributes with constant linear density distribution. We see how mass concentrates at the end. So we will like do research how the both like ends changes with time when we try to follow the Slinki, as well as putting all of this in the stationary initial position, and later use like our special methods to release it without increasing external forces. And we want to analyze the interesting nature of sound propagation in metal, as well as like wave propagation in metals, as well as how its velocity and coordinate depends on time. So we'll do experiments for both different lengths, as well as doing the experiment multiple times, so we could cross-validate the consistency of our results and make the error analysis. In total, we'll make around like 3 measurements for every length we take, as well as 3 measurements to each of them, and 3 different lengths. So we will do the whole length. Later we will take 2/3 and 1/3, and we record every video on our iPhone 15 with in slow motion regime with 140 FPS, frames per second. And later I use the tracker system to get the dependence of coordinate and velocity on time to later match to our theoretical predictions that we will overcover in this video. To release the object without any to minimize the external forces for the object, we'll use a string about 1 or 2 millimeters in thickness, as well as fire. The fire is used as the easiest way to remove to remove the string, because we use both electricity to make like fire and as well as connection to the LED. However, it wasn't the safest possible option, so we just put fire on the string, and it melts. As well, so we connect this Slinki to the end of the to the ceiling of the TE room, and we monitor how it falls. So now I suggest to move to the quantitative description of what is going on, and later I will cover the theoretical prediction. And we show the experimental results that we obtained based on the recording of video and tracking the falling Slinki. And afterwards, I will show the comparison of the experimental results and the theoretical predictions that we obtained. We'll make the conclusion and show and validate our theory. Thank you. Okay, very well. So now I will tell a little bit about the theory that is going on here. So initially we set x-axis from down to up, and let's call it y-axis. It's a vertical position. In our model, we set the continuous equation described by this equation, where the speed of wave could be found by the ratio of k over mu. So here we take the double derivative by time and multiply the second derivative by partial derivative by coordinate multiplied by the speed of wave distribution, and this is equivalent for the continuity equation. We set the boundary condition for the free ends, and and the speed with which signal moves, like our wave, is determined by c. Thus, the time that the wave transitions from one end to another is L over C, where L is the length of the Slinki. So the center of mass could be defined by the integral of the second derivative by time of y over dx. And later we cross-validate the we solve the partial those differential equations for the segment. So we discretize our system by n discrete units, and later we set the differential equations for like nearby units. So we consider how forces interact on the upper and lower end for each segment, and later we make the prediction for this, like the speed at which the wave distributes. Later we uh, compare our prediction to the experimental data, as well as based on this discrete ordinary differential equation, we compare it in our simulations, and that I will show you later. First of all, let's validate the theory. We make the simulations on Python. We solve this differential equation and see how both ends of the Slinky moves. And as a result, we see when we release the Slinky, only the upper end is moving and the lower end stays in the same stationary position. And later, when the upper end reaches the lowest end, they start moving together. This is the known results from the experiments. Let's plot the position of both ends from time and see how it matches with our experimental results. Here I will show you how I track the data. So first of all, I determine the axis where the video tracking will be going. I using the open source tracker software. I set the sticker. It's set to 0.8 from 10 to 90 centimeters. Uh, and later I analyze the data frames. So here how it looks like in real time. So it's video recorded in 140 fps. So here is the results of the tracking, and we see the dependence of the position of from time, instant velocity and acceleration. We see those jumps in velocity acceleration because they're instant, and the tracker is not perfect. So, but the quality of figure of the position versus time is um, similar what we see in the simulational part. By the end, I would like to say that like both our simulational and the experimental results showed the predictions that was based on our theory, and the quantity of behavior of the position showed a great correlation, and the more information will be provided on the website, as well as the final presentation that will be on Friday. So I welcome everyone to watch the final presentation. Thank you.